Geometry is the study of shapes, sizes, relative positions of figures, and the properties of space. It's not just a math class concept, it's a fundamental aspect of the world we live in. Look around and you'll see geometry in buildings. Rectangles form walls and floors, triangles create stable roofs and supports. In nature, geometry appears in patterns like the hexagons and bee honeycombs, which efficiently use space and provide strength. Artists use geometric shapes like circles and squares to create balance, symmetry, and visual harmony in their work. Geometry is crucial in architecture for creating buildings that are stable, functional, and aesthetically pleasing. Architects apply geometric principles to ensure structures stand strong and look harmonious. Architects use key geometric principles like symmetry for balanced designs, proportion for correct ratios, and spatial reasoning for planning three-dimensional spaces in blueprints. The pyramids of Giza use triangular geometry for structural stability. Modern skyscrapers employ rectangular grids and symmetry for efficient, strong designs. Engineers use geometry extensively to ensure the structural integrity of buildings, bridges, and tunnels. Geometric shapes like triangles and arches distribute weight efficiently and provide stability. Triangles are rigid and stable. Unlike squares or rectangles that can deform, triangles maintain their shape under stress. Engineers use triangular trusses in bridges to distribute weight evenly across the structure. Arches work by converting vertical loads into horizontal compressive forces. The curved shape directs weight along the arch to the supports, creating a stable structure that can span large distances. In truss bridges, engineers connect structural elements in triangular patterns. These triangles create a framework that efficiently carries loads from the roadway to the supports, preventing collapse under heavy weight. Arch bridges use the strength of the curved arch to support the weight above. The arch pushes outward against the supports, creating compression that holds the bridge together without additional reinforcement. By applying geometric principles, engineers create structures that are not only functional, but also safe and durable, supporting our modern infrastructure. The golden ratio, approximately 1.618, is a mathematical proportion that creates visually pleasing compositions. Artists and designers use this ratio to achieve balance and harmony in their work. A golden rectangle has sides in the ratio of 1 to 5. When you divide a square from it, the remaining rectangle maintains the same ratio, allowing for a continuous spiral. The Mona Lisa by Leonardo da Vinci incorporates the golden ratio in its proportions. The Apple logo also uses this ratio in its circular design. Geometric patterns like tessellations create repeating shapes that fill space without gaps. Fractals are complex patterns that are self-similar at different scales. GPS technology relies heavily on geometry to determine your exact location anywhere on Earth. GPS uses a network of satellites orbiting Earth. These satellites continuously transmit signals that GPS receivers on the ground can detect. A GPS receiver calculates its distance from each satellite by measuring the time it takes for signals to travel from the satellite to the receiver. Each distance measurement defines a sphere around the satellite. The receiver's location is where these spheres intersect. This geometric technique is called triangulation. Once the position is determined, it's expressed using latitude and longitude coordinates. Latitude lines run parallel to the equator, measuring distance north or south. Longitude lines are meridians that measure east or west from the prime meridian. Urban planners use geometry to design efficient and organized cities. Geometric shapes create logical street patterns that improve navigation and functionality. Grid layouts, like in Manhattan, use straight intersecting streets to create rectangular city blocks. This geometric pattern makes navigation predictable and allows for efficient land use. Circular layouts seen in cities like Paris use concentric rings connected by radial streets. This pattern distributes traffic flow evenly and creates natural centers for public spaces. Radial layouts, like Washington, D.C., feature streets that radiate outward from a central point. This design creates focal points and can improve accessibility to key areas. Geometric planning improves cities in several ways. Organized street patterns enhance traffic flow by reducing congestion, increase accessibility through predictable navigation, and improve livability by allowing efficient allocation of space for essential services. Nature displays remarkable geometric patterns that optimize efficiency and stability. From honeybee architecture to plant growth and crystal formation, mathematics governs these natural designs. Honeybees construct hexagonal cells in their hives. The hexagon's 120-degree angles and equal sides create a shape that uses the least wax while providing the most storage space. This geometric efficiency is why bees choose this pattern over squares or triangles. Sunflowers arrange their seeds in spirals following the Fibonacci sequence 1, 1, 2, 3, 5, 8, 13, 21. This mathematical pattern ensures maximum seed density, allowing each seed to receive sunlight and nutrients without crowding. The golden ratio emerges naturally from this sequence. Snowflakes form with perfect six-fold symmetry due to water molecule geometry. Each snowflake is unique, yet all follow the same hexagonal crystal structure. This symmetry provides structural stability as water freezes, creating intricate patterns that maximize surface area for efficient growth. These natural geometric patterns, from beehives to plant growth and ice crystals, demonstrate how mathematics optimizes efficiency, stability, and resource use in the living world. Geometry is nature's universal design language. Geometry is essential in robotics, enabling machines to navigate environments, recognize objects, and manipulate items with precision. For navigation, robots use geometric algorithms to calculate distances between points using formulas like the Euclidean distance and determine optimal paths to avoid obstacles. Autonomous vehicles, for example, use geometry to plan routes around obstacles, calculating angles and trajectories to reach destinations safely. In object recognition, robots analyze geometric properties like shapes, sizes, and orientations to identify and classify items in their environment. For manipulation tasks, robots use inverse kinematics to calculate joint angles and trajectories needed to grasp and move objects with accuracy. Robotic arms in manufacturing use geometric calculations to assemble components, following precise paths to connect parts efficiently. Through geometric principles, robots can navigate spaces, recognize objects, and perform complex manipulations, making them invaluable in modern technology. Computer graphics use geometry to create realistic 3D images and animations by breaking down objects into basic building blocks. Points are the simplest elements, representing locations in 3D space with coordinates. Lines connect points to form edges and outlines. Polygons, especially triangles, fill surfaces and create the visible parts of 3D objects. Software combines these primitives to construct complex 3D shapes. For example, a cube is made from points connected by edges into faces. The rendering process applies geometric transformations and lighting calculations to convert these wireframe models into realistic images. Geometry enables smooth animations by calculating transformations between frames. This cube rotates using geometric matrix operations. These geometric principles allow computer graphics to create everything from video games to movies, all built from points, lines, and polygons in virtual space. Medical imaging techniques like MRI and CT scans rely heavily on geometry to analyze the shape and size of organs and tissues within the body. These scans create cross-sectional images of the body where geometric shapes represent different anatomical structures. Doctors use geometric measurements such as diameter and area to assess organ health and detect abnormalities. For example, an irregular shape compared to the expected circular or elliptical form can indicate disease. Geometric measurements also help monitor treatment progress, tracking changes in size and shape over time. This geometric analysis enables precise diagnosis and effective treatment planning in medicine. Geometry plays a crucial role in astronomy, helping us understand the positions, distances, and movements of celestial objects throughout the universe. Astronomers use geometric coordinate systems to precisely locate objects in the sky. The celestial sphere concept treats the sky as a giant sphere with geometric grids for measuring positions. Each star and planet has precise geometric coordinates, allowing astronomers to track their movements and predict their positions. The movements of planets and stars follow geometric paths. Orbits are elliptical, and their positions can be calculated using geometric formulas. One of the most important geometric techniques in astronomy is parallax, which measures distances to nearby stars by observing their apparent shift against distant background stars. Astronomers use geometric analysis to study complex structures like galaxies. By measuring angles, distances, and symmetries, they can understand the formation and evolution of celestial objects. In manufacturing, geometry ensures that components fit together precisely. Every part must meet exact specifications to function correctly in assemblies. Geometric tolerances define the acceptable variations in a part's shape and size. For example, a shaft might have a tolerance of plus or minus 0.1 millimeters. Various tolerance types exist, such as flatness, which ensures surfaces remain level. These specifications prevent manufacturing defects and maintain product quality. Fashion designers rely on geometric shapes as the foundation for creating clothing. Triangles, squares, and circles provide the basic forms that garments are built upon. Proportion ensures garments fit the human body harmoniously. Designers use geometric ratios to create balanced silhouettes that complement different body types. Symmetry creates balanced, formal designs where the left and right sides mirror each other perfectly. This creates a sense of order and elegance in clothing. Asymmetry introduces intentional imbalance, creating dynamic and modern looks that break traditional patterns and add visual interest. Triangle shapes create skirts with a wide base that allows freedom of movement while maintaining an elegant silhouette. Square collars provide structured, professional looks that frame the face and create clean lines in shirt designs. Circular patterns soften garment designs, creating flowing, organic shapes that add texture and visual interest to clothing. By applying geometric principles of shape, proportion, symmetry, and asymmetry, fashion designers create clothing that is both functional and aesthetically pleasing. Geometry forms the foundation of game development, enabling everything from character movement to level design. Game engines rely on geometric shapes and algorithms to create immersive, interactive worlds. In game development, the world is built using geometric shapes. Characters and objects are represented as simple forms like rectangles and circles, which make calculations efficient. Collision detection uses geometric algorithms to check if objects overlap. Game engines employ bounding boxes or circles around objects to simplify these checks. Geometry guides character movement and physics simulation. Algorithms calculate paths, detect obstacles, and simulate realistic interactions like bouncing or stopping. Level design relies on geometric shapes to create navigable environments. Platforms, walls, and obstacles are positioned using coordinates and shapes for precise gameplay. Cartographers use geometry to transform the curved surface of Earth into flat maps. The challenge is that representing a three-dimensional sphere on a two-dimensional plane requires mathematical transformations called map projections. The Mercator projection is widely used for navigation. It preserves angles and shapes locally, making straight lines on the map represent true compass directions. However, it dramatically distorts sizes near the poles. Equal area projections, like the Peters projection, preserve the actual sizes of land areas. This gives a more accurate representation of relative sizes, but shapes become distorted, especially near the edges. The Robinson projection offers a compromise, with minimal distortion in the center and moderate distortion at the edges. It balances shape and size preservation, making it popular for general reference maps. No map projection can perfectly represent Earth's curved surface without distortion. Cartographers choose projections based on the map's intended use, balancing the trade-offs between shape, size, and directional accuracy. Surveyors use geometric instruments to precisely measure distances, angles, and elevations on Earth's surface. This data creates accurate maps and property boundaries, essential for construction, land development, and legal purposes. A theodolite measures horizontal and vertical angles. It consists of a telescope mounted on a rotating base that can pivot both horizontally and vertically, allowing precise angle measurements between survey points. The total station combines angle measurement with electronic distance measurement, or EDM. It sends laser or infrared signals to a reflector prism, calculating distances based on the time for the signal to return. Surveyors also measure elevations, or height differences, using the vertical angle capabilities of these instruments. This creates topographic data showing the three-dimensional shape of the land. Surveying data creates accurate maps and defines property boundaries. This information is crucial for construction planning, legal land ownership, and infrastructure development. Geometry plays a crucial role in sports, from calculating the perfect trajectory of a ball to designing the precise layout of playing fields. In ballistics, geometry helps calculate optimal trajectories. For example, a soccer player needs to consider the launch angle and initial velocity to curve the ball into the goal. Playing fields are designed using geometric principles. A basketball court uses rectangles for boundaries and circles for the half-court line, ensuring fair play and precise measurements. Athletes use geometric principles to improve performance. In basketball, understanding the optimal shooting angle of about 45 degrees helps players make more accurate shots from various positions. Geometry plays a crucial role in data visualization, where geometric shapes and arrangements transform raw numbers into meaningful visual stories that are easy to understand and analyze. Bar charts use rectangular bars of varying heights to represent different data values. The length or height of each bar corresponds to the quantity it represents, making comparisons quick and intuitive. Pie charts divide a circle into sectors, where the angle of each slice represents a proportion of the whole. This geometric approach helps viewers understand parts-to-whole relationships at a glance. Scatter plots use individual points plotted in a two-dimensional coordinate system to show relationships between variables. The geometric arrangement reveals patterns, correlations, and trends in the data. By leveraging geometric principles, data visualizations transform abstract numbers into visual narratives that highlight patterns, comparisons, and insights that might otherwise remain hidden in raw data. Investigators use geometry to reconstruct crime scenes and analyze evidence. By measuring distances, angles, and trajectories, they can determine how events unfolded and identify key evidence. One fundamental technique is measuring distances between evidence points. For example, the distance from a bullet hole to the victim's position can help determine the shooter's location. Angles are crucial for analyzing trajectories, such as bullet paths or blood spatter patterns. The angle of impact can reveal the direction from which a shot was fired or how a victim fell. Crime scene diagrams use geometric annotations to document evidence, locations, and relationships. Lines show trajectories, arcs indicate angles, and measured distances help build a complete picture of what occurred. Geographic Information Systems, or GIS, are powerful tools that use geometric principles to organize and analyze spatial data. GIS combines location data with descriptive information to create detailed maps and perform complex spatial analyses. At the foundation of GIS are geometric primitives that represent real-world features. Points mark specific locations like buildings or landmarks. Lines represent linear features such as roads or rivers, and polygons define areas like land parcels or water bodies. GIS performs spatial analysis using geometric operations. For example, buffering creates zones around features, overlay operations combine different data layers, and proximity analysis measures distances between objects. These operations help solve real-world problems. In urban planning, GIS uses geometric analysis to optimize city development. Planners can analyze zoning patterns, transportation networks, and population density to make informed decisions about where to build schools, parks, and infrastructure. Environmental managers use GIS to monitor natural resources and track changes over time. Geometric analysis helps identify protected areas, track wildlife habitats, and assess environmental impacts from development projects. During disasters, GIS provides critical geometric analysis for emergency response. Flood mapping, evacuation routing, and resource allocation all depend on accurate spatial data and geometric calculations. GIS transforms geometric data into actionable insights for diverse applications. By combining spatial geometry with analytical tools, GIS helps professionals make better decisions in urban planning, environmental protection, and emergency management. In microscopy, scientists use geometric analysis to measure the size and shape of microscopic objects like cells and bacteria. By calculating dimensions such as diameter, length, and width, researchers can identify different types of microorganisms. For example, a spherical cell has a measurable diameter that helps determine its size. The geometric shape provides clues about its function and type. A rod-shaped bacterium can be measured for both length and width, creating a distinct geometric profile. These measurements allow classification into different bacterial categories. By analyzing these geometric characteristics, scientists can distinguish between various microorganisms and understand their biological properties. Seismologists use geometry to locate earthquake epicenters through a technique called triangulation. When an earthquake occurs, it sends out seismic waves that travel at different speeds. Seismic stations around the world detect these waves. By measuring the time difference between the arrival of P waves and S waves, scientists can calculate the distance from each station to the earthquake's epicenter. Using at least 3 stations, circles are drawn with radii equal to these distances. The point where the circles intersect is the epicenter. This geometric method precisely pinpoints where the earthquake began. Throughout this exploration, we've seen how geometry permeates every aspect of our world. From the buildings we live in, to the technology we use, from the natural patterns around us to the art that inspires us, geometry provides the foundation for understanding and innovation. Geometry enables advances in architecture, engineering, urban planning. Geometry enables advances in navigation, computer graphics, medicine. Geometry enables advances in nature, art and design, astronomy. Geometry enables advances in manufacturing, sports, data visualization. Geometry is not merely an abstract mathematical concept. It is a fundamental tool for understanding and shaping our world. Every structure, every device, every natural form relies on geometric principles. As you go about your day, take a moment to observe the geometry all around you, in the symmetry of a building, the curves of a road, the patterns of nature. Geometry truly is the language of our world.